So yesterday we solved our first differential equation, just to kind of play around with it. And we ended up with something that looked, it was kind of ugly, but it wasn't the worst it could be. It looked something like that, give or take. Although I think that was supposed to be a T. But they don't always turn out this pretty. Sometimes when you solve your differential equation, you end up with an integral in it, such as happened in number 21 for the journal. So do we need to do number 21, or did everybody understand it? Can we do it? Yes, we can do it. I have to find it. Worked out journal problems. 13, 15, 21. All right, so it says, solve the initial value problem using the fundamental theorem. Your answer will contain a definite integral. So we've got dy dx is equal to sine x squared. And we do have a point. We know that y is equal to 5 when x is equal to 1. And so let's just review for a minute here what the fundamental theorem of calculus tells us. Okay, the fundamental theorem of calculus says that if we take df dx of my integral here from a to x of f of t dt, that's going to give me f of x. Okay. And then we can compare that with what we're given. So this part here is going to be dy dx. This part over here is going to be sine of x squared. And a is going to be equal to 1, because that's what we were told. Okay. All right, we got it? We good? Everybody write down what they need to write down? Okay, so that means that what we're really solving here is dy dx is going to be d by dx of the integral from 1 to x of, remember I turned my x's to t's, sine t squared dt. And basically, I want to solve for y. That's what I'm looking for. So I'm going to take the antiderivative of both sides. And when I take the antiderivative of dy dx, what do I get? Y. And when I take the antiderivative of that, what do I get? Times t squared dt. Yeah, okay, because what I'm basically doing when I take the antiderivative here is I'm just getting rid of the d by dx part. But am I done? What do I have to write? Plus c, because I don't know what that constant is. It could have been something, it could not be something, I don't know. But of course, I want to figure out what C is, and I can do that because they gave me a point. Remember we talked about how this is a general solution, this is a family of solutions, but I can pick out the particular solution if I have a point. because this is going to give me a whole bunch of curves that are kind of parallel to each other, although they're not straight lines. They look concentric again. They're not quite circles. And I want to pick out the one that's going to be the specific solution to my problem. So I use my initial condition, which says that when x is equal to 1, what's y equal to? 5? Okay. Yes, what I was going to say, this is what Zoe and I were talking about first period. What's that integral going to be equal to? 0. And it works that way by design. So what's c equal to? 5. You're not really picking what a is. You're usually given the point. And so you want a to be equal to the x value of the point. Or you want x to be equal to whatever you had for a, so that that difficult thing goes away. Okay, so that means then that our final answer is y is equal to the integral from 1 to x sine of t squared dt plus 5. Okay. Does that help? Make us feel good? We got it? All right. And that's ugly. No question about it. But it is, in fact, a valid answer. If you can evaluate that integral, you should. I don't honestly know offhand how to do that. It might be in the integral tables in the back of your book. But this is the answer that you're allowed to have. Okay? We good? We got it? All right, so let's move on to we're going to move a step closer to slope fields, because an important segue to slope fields is drawing the graph of the function using the differential equation. And the important thing to remember is that dy dx is the slope at a point, at any point. Okay. So I'd like to look at, which again I think was part of the journal, page 331 to 332, number 25 to 28. If somebody would read that for us, please. Okay. So I find it very strange that they broke this between 2 pages the way they did. They're laying out the book and they have moved something around here. So we've got 4 equations. So number 25 is dy dx is sine x squared. 26 is dy dx is equal to sine x whole thing cubed. 27 is dy dx is equal to cosine x whole thing squared. And 28 is dy dx is equal to cosine x whole thing cubed. Okay. So we want to take those functions and somehow match them to graphs A, B, C, and D, which are on the next page. And so you know that my job is to help you learn how to solve problems. And one of the ways I do that is by giving you examples. And another way that I do that is by giving you techniques and telling you things that I think you should do. So when you have to solve a problem like this and you're going to compare slopes from this to a whole bunch of graphs, I think it's a good idea to make a table. And you know how much I love a good table. Okay, so I'm going to rewrite these over here real quick. Okay. So because we're dealing with trig functions, we're probably going to be interested in what the values of these slopes are at like 0 and pi over 2 and pi and negative pi and 3 pi over 2 or negative pi over 2. So let's make a big table here. And it's going to be the dy dx values, or the slope. And we're going to write out each function that we have. And then we're going to pick some values, like I said. Values that will be convenient for us to determine. That was really cool. Not. Let's see if we can bring that back over there. So we're going to be interested in 0. Because these are trig functions, probably pi over 2. Because our graph goes on both sides. If you look at options A, B, C, and D, it goes to the left and the right of the origin. And 3 pi over 2 or negative pi over 2. So the way we're going to do this is pick some values, figure them out, fill them in on the board. Go! Everybody's got to do at least one, and half of you will have to do a second one. No. Oh. No, calculators are not allowed. Sarah, put your calculator away. For crying out loud, it's the sine and cosine of multiples of 90. You should be able to do it in your head. It's a survival skill. I'm good with that. You can do up to 2. And then walk away. This is the only thing that in this point of the year I will make fun of you if you can't do. Okay? It's just reality, because you need to know how to do it. Yes, Casey. For crying out loud. Yes, it's one. Oh, my word. Your peers should be able to tell you whether you're right or wrong. This is ridiculous. And it's not that hard. And everybody's using the same color. Let a little color into your lives. Get wild. It's kind of Maddie's thing, is to go against the grain.
I can't look at it anymore.
wait a minute, Alf. Wait. What's the cosine of pi? Cosine of pi is -1, so you're going to square it. There you go. I didn't have a problem with the first one. It was the second one. Guys are crazy. No. What's the cosine of pi over 2? It doesn't matter if you do 3 pi over 2 or negative pi over 2. It's still the same thing. What's the cosine of 90? No. She'll figure it out. Look at the pattern. What was the cosine of pi over 2? 0. So what should the cosine of negative pi over 2 be? And if I cube 0, I still get, there you go. Okay. All right. So are we good here? We got the right answers? Okay. So now we have to compare them to the graphs, which you should have in front of you. So if you don't have a book, scoot over so that you're looking on with somebody who has a book, or go get a book from the shelf. Okay. So I would start by looking at the origin here. Okay, so if you look along the y-axis, which of those graphs has a slope of 0? A, B, C, or D? And B. Okay, so these two could be B or C. All right. Now, if we go to the right, we might look here at what might be pi over 2. But the bottom line is we have another 2 graphs here that should have horizontal lines a little bit to the right of the origin. So which of those graphs has a horizontal line as we go to the right? A and D. So these are A or D. So now what are we going to do? What about the negatives? Negative slope. Okay, so for instance, if we look at the sine x cubed, the slope on the right side of the origin is positive, but the slope on the left side is negative. So if you look at B and C, which one has a positive slope on the right and a negative slope on the left? Okay, so we want to say that sine x quantity cubed is C. So let's just check here for a minute. If we look at sine squared x, we should have positive slopes on both sides of the origin. Is that what we've got for B? Okay. And then we can do something similar when we've got cosine x quantity cubed. The sign of the slope changes between the origin and a little farther on. So if we look at A and D, which one has the slope being the same? And which one has the slope changing? A's what? Because that, Sarah, that's what you said, that A had the slope not changing, right? Oh, okay. Well, A has the slope that doesn't change, and that's what's going to happen with the cosine squared, which means that cosine x quantity cubed is going to be D. Okay? Everybody understand how to put these pieces together? All right. I really feel that a table helps immensely. For many of the slope fields, a table, as you'll see, is going to be very helpful. Did everybody do exploration 1? Let's see, what time is this class going to end? 9:40. So we've still got 8 minutes. Okay. Sure. So let's try slope fields. And we have to do the problem too. Okay? So, slope fields. I find in general that people have issues with understanding what a field is. Okay. Have you come across a field yet? Nope. Have you come across a field in a science class? Like a magnetic field. Okay. You know of any other? Magnetic field's a pretty good example. Do you know of any other fields? There are electric fields. You are existing right now in a gravitational field. Okay. So the way I think about fields is they're a set of instructions. And those instructions exist whether you're using them or not. So if I drop the pen, what's going to happen? Why is it going to fall? Gravity's going to pull it down. Okay. The gravitational field says pull down on the pen. Is gravity pulling down on the pen right now? Yeah. Yes. Sarah, you should be shaking your head. Don't scare me. Okay. The gravitational force is pulling down on the pen right now. This pen exists in a gravitational field. That instruction to pull the pen down exists whether the pen is here or not. It exists whether I'm pushing up on the pen or whether I'm not. So all around you, going through you, is this gravitational field that says pull down on stuff. Pull stuff towards the center of the earth. Okay, but like I said, that field exists right here whether there's something for the pen to act on it or not. And what happens is you put something there, and then the field says, well, hey, what you're supposed to do is be pulled down. The same thing works with a magnetic field. Have you ever used a compass? Everybody know what a compass is? Oh yeah, let's not talk about that. Okay, she's got her own very strong magnetic field. All right, so not the kind that you draw circles with, but a compass that has a needle on it. Yes, have you seen one, Elf? No? It's a compass. Okay, and what is and it tells you north, south, east, and west. What does the needle do? Anybody? Maddie. Actually, what it does is it aligns itself with Earth's magnetic field. It is in fact a magnet. Magnets are dipoles, not monopoles, so you always have to have a north and a south. We're not going to get involved with where magnetic north is. But this will line itself up with the magnetic field. The magnetic field exists whether I'm holding my compass in my hand or not. The magnetic field is going through you. It's a set of instructions. It says, hey, if I put a compass here or a magnet that's free to move around, line up with north. Okay? There are birds that you have, do they have magnetite? They have some kind of mineral in their heads that tells them which way is north and south, so they know which way to go when they migrate. They have like tiny little free magnets in their heads that line up. But that magnetic field exists whether the bird is there or not. Okay, so fields are kind of weird. But a field is a set of instructions that exists everywhere. And then if you put something there, it says, okay, this is what you're supposed to do. Okay? So, I have two windows there. That's going to be what a slope field is it's going to be information about the direction of the slope at any point. Whether I have an object there, whether I care, it's going to be there. I could count, well, it's going to be, so for instance, we're obviously not going to get through it, but we're going to start page 332, number 32, okay? And it tells you to construct a slope field for the differential equation. And the differential equation that you have is dy dx is equal to 2x minus y. So using that equation, I'm going to be able to calculate the slope at any point that I want. This also represents the slope at every point or at all the points. I just have to put in the x and y value that I'm interested in. And usually when there are problems like this, what they want you to do is they're going to give you a grid of points. So here you're going to go from -1 to +2 in x. You're going to go from -1 to +2 in y. And you take each of those individual, I've got a grid of, 16 points here, because of course I've got everything on my axes too. Okay, so it's going to say, draw the tiny little slopes that would be at each of these points. So I'm going to take a set of points off of here, substitute the x and y values into my grid, and then draw it. So for instance, here at the origin at 0, 0, what's my slope? 0, right? So I make a tiny little horizontal line. What's my slope going to be at 1, 1? 1. Okay, so we'll work with this again tomorrow. And again, there's going to be a table. Gotta love a good table. I do.